this lecture I will discuss predicate and quantifiers. You might have read the sentence in English. The sentence consists of two parts, subject and predicate. Subject, for example, x is greater than y, and x is a subject and is greater than y. Is greater than is a predicate. Now I will discuss it in the mathematically, and what are the applications of predicates and quantifiers we will discuss in this lecture. Propositional functions and predicates. First, propositional functions means open sentence. Open sentence means a statement involving one or more variable. For example, x minus 3 is greater than 5. Let us call this propositional function px, where p is predicate and x is the variable. Then what is the truth value of p2? That means when x is 2, then x equal to 2 is 2 minus 3. 2 minus 3 means minus 1 is greater than 5. This is false. Hence, this is false. Similarly, p8 means 8 minus 3 is equal to 5. 5 is greater than 5. It is again false. p9, now here 9, x is 9, 9 minus 3 is 6. 6 is greater than 5. Hence, it is true. When a variable is given a value, it is said to be instantiated. Hence, this is a formula, or this is a statements, propositional functions. This is a propositional functions, and these are the instantiations with different values. Truth value depends on the value of the variables. Let us consider the propositional functions q, x, y, z defined as x plus y is equal to z. Here q is the predicate and x, y, z are the variables. What is the truth value of q2, 3, 5? It is true, since 2 plus 3 is equal to 5. What is the truth value of 0, 1, 2? It is false. What is the truth value of 9 minus 9, 0? It is true. A propositional functions, that is predicate, becomes a proposition when all its variables are instantiated. Since here it is all the variables are instantiated, 2, 3, 5, hence it is called a propositions, and this is called a propositional functions. Other examples of propositional functions: person x, which is true if x is a person. If we write x is a person, then using propositional functions we write in this manner: person bracket x. Now, and it is instantiated with Socrates. Socrates was a person, hence person Socrates is true. Whereas person Dolly the sheep, Dolly is the name of a sheep, hence it is a false statement. CS course X, which is true for X is computer science courses. If CMSC is a computer science course, then it is true. On the other hand, Math 1 55, it is false, since it is not a computer science course. How do we say all humans are mortal? One CS course. Universal quantifications is needed for these things. Let Px be a predicate or propositional functions. Universally quantified sentence will be, for all x in the universe of discourse, Px is true. For example, the square of any integer is greater than the integers. It is true for every integers. Hence, we can write that for all x, x square is greater than x. This is the universe of discourse. The x, the variable x, have value from minus infinity to plus infinity, which consist of all the integers. Using the universal quantifier, this is universal quantifiers and it is read as for all. Suppose that there is a statement Px, and if for all x a symbol is attached, then we can read in this way: for all x Px, or for every x Px. That means for all x Px is true. Note, for all x Px is either true or false, so it is a proposition, not a propositional functions. Universal quantification. Example, let the universe of discourse be all people. Sx, x is the computer science student, and gx is x is genius. Then what does the statement means? That is, the statement means that if x is computer science student, then x is genius, or all computer science student are genius. Now we can write the statement in this way: if the universe of discourse is all computer science student, then the same statement can be written as for all x gx. That means for all x, for all the computer science students, gx will be gx means the students is genius. All the computer science students are genius. That means for all x gx. Universal quantifications, another examples. For example, what is a truth value? What is the truth value of for all x Px, where Px is a statement such that x square is less than 10, and the domain consists of 4 positive numbers. The statement for all x Px is same as conjunctions. That means P1, P2, P3, P4. For P1 it is true, for P2 it is true, for P3 it is true, but for P4 it is false. That means 4 square is less than 10 is false. Hence, by conjunctions, the rule of conjunctions, this statement will be false. Existential quantifications. There exists an x in the universe of discourse for which Px is true. Using existential quantifiers, this is the symbol of existential quantifiers. It is read as there is an x such that Px, there is at least one x such that Px. There exists x Px is either true or false, so it is a proposition, but not propositional functions. Example, Px is a statement that x is computer science professor. EGX, that means x is genius. What does this statement means there is an X such that X is a computer science professor and X is genius. This is AND operator. So there is an X such that X is a computer science professor and X is genius. Or at least one computer science professor is a genius. Another example, what is the truth value of there exists X such that Px, where Px is the statement such that x square is greater than 10, and the universe of this course consists of positive integers not exceeding 4. This is because the domain is 1, 2, 3, 4. Since the integers, it is a positive integers and less than not exceeding 4, therefore domain is 1, 2, 3, 4. And the propositions is there exists Px is the same as disjunctions. Disjunctions means or. When we use there exist operator, it is a disjunctions. It is a statement of disjunctions. That is, we use or operators. In the case of or, any one of the statement is true, then the statement then the result will be true. Here the statement P4 is true, since 4 square is greater than 10 is true. Hence other statement, though they are false, but the resultant is true, hence the statement is true. Hence this propositions is true. Disproved by counterexample. A counterexample to this statement, for all x Px is an object C so that Pc is false. A statement such as Px implies Qx can be disproved by simply proving a counterexample. All birds can fly. Disproved by counterexample, penguin. Now negations. Negation statements, that means when we use negation operator for there exists x Px, it will be for all x and not Px. This is the equivalent statement. When is negations is true, for every x Px is false. When false, there is an x for which Px is true. This is true statement and this is false statement. Similarly, when we use negations operator for all x Px, it will be there exists x not Px. When is negations is true, there is an x for which Px is false. When false, Px is true for every x. Example, not all roses are red. This can be written as not for all x, rose x implies red x. Now negations operators, using negation operator, it become for there exists x, and when this implies statement is changes to conjunction operator, by using equivalent statement it become rose x and not red x. Nested quantifiers. For example, the statement it is read as for all x there exists a y such that x plus y is equal to 0. Here is two variables x and y, and the two variables ranges from have different ranges. For example, such that x for all x, that means if we take any value, integer value, take an integer value 2, then there exists y, that is minus 2, such that x 2 minus 2 is equal to 0. In this way, for all x there exists y such that x plus y is equal to 0. If there is more than one variable, we use nested quantifiers. That means we use a group of quantifiers for different variables. For example, the sum of two positive integers is always positive. We can write it as follows: for all x and for all y, such that x is greater than 0 and y is greater than 0. It implies that x plus y is greater than 0. If the two numbers is positive, definitely the sum will be positive. Associative law for additions. This can be also represented as nested quantifiers. Here all the quantifiers are universal quantifiers for all x, for all y, for all z. X plus y plus z is equal to x plus y plus z. Translate into English sentence. Suppose that this is a statement. This is a given statement: for all x, for all y, x is greater than 0 and y is less than 0, implies x, y is less than equal to less than 0. What is the meaning of the statement? Here the domain for both variable consists of all real numbers. The solution is, the statement says that for every real number x and for every real number y, if x is greater than 0 and y is less than 0, then xy is less than 0. That is, this statement says for real numbers x and y, if x is positive and y is negative, then xy is negative. That means the product of the statement will be the product of positive real number and negative real number is always a negative real number. A predicate can have more than one variable. Suppose that x is xyz. Xyz, this is a predicate. Z is the sum of x and y. If xy is x and y are friends, then we can make some statement using nested quantifiers like this. We can quantify the individual variables in different ways. For example, for x, y, z, for all x, y and z, is x, y, z, that means x plus y is equal to z, implies that x is less than z and y is less than z. That statement means if the sum of for all x, y, z, if x plus y is equal to z, then definitely x is less than z and y is less than z. Second statement can quantify the predicates. There exist a x there for all y and for all z. Here x, y, z are human being. If we have to make a sentence like this: the y and z is not a friend of each other. Then we can make this sentence, the statement f x y, that means x and y are friend and x and z is friend and y is not z. Then definitely statement says that f y not f y z, that means y is not a friend of z. Another example exercise: translate the following English sentence into logical expression. There is a rational number in between every pair of distinct rational number. Qx denotes the x is a rational number. We define a formula for this using nested quantifiers. Now here for all x and for all y, Qx, that means x is a rational number, Qi means Qy is a rational number and x is less than y. If all are true, then it implies that there exists a value u, that is u is a rational number, that is u is a rational number and x is less than y and u is less than y. That means u lies between x and y. So if this is true, then it implies that there is exist a rational number between x and y. In this lecture, we discuss propositional functions using quantifiers, universal and existential quantifiers. When predicates become propositions, all of its variable, how it is instantiated, all of its variables, how it is quantified, nested quantifiers, quantifiers with negations, logical expressions formed by predicate operators and quantifiers. Thank you.